So what if I told you we could tackle one of the biggest problems on the planet? I'm talking about water pollution with a solution so ridiculously small you can't even see it. Well, today we're diving into some incredible tech that uses tiny, light-powered engines to literally just annihilate some of the most stubborn pollutants out there.
Okay, so where is all this pollution coming from? You know, every single year, industries like textiles, pharmaceuticals, they release this cocktail of chemicals into our water. Things like synthetic dyes, leftover bits from drugs. The scientific name for them is persistent organic pollutants, or POPs. And yeah, as that name suggests, they are built to last.
And that's the real kicker. These aren't just any old contaminants. No, these things are tough. Your traditional cleanup methods like, say, biological treatments or even fancy membrane filters, they just don't work very well. Or it's just wildly expensive and takes a ton of energy. So these forever chemicals just hang around, building up in the environment and causing some serious problems for everyone.
So, how in the world do you fight a problem this persistent? Well, you don't just try to filter it out. You have to destroy it. And the key, as it turns out, is light itself. The hero of our story is this process called photocatalysis. Now, I know it sounds super complex, but the idea behind it is actually beautiful in its simplicity. You've got this special material, a catalyst, and when light hits it, it just springs into action. It gets all energized and starts creating these incredibly reactive agents that basically hunt down and just obliterate the pollutants. Seriously, it's like an army of microscopic sun-powered cleanup bots.
Let's walk through the battle plan here. Step 1, the nasty pollutant gets stuck to the catalyst. Step 2, bam! Light strikes it. This creates this little burst of energy. Think of it like charging up a tiny battery inside the particle. Step 3, that energy creates these powerful superoxidants, which are basically microscopic weapons. And finally, step 4, annihilation. The weapons attack the pollutant, shattering its molecular structure into completely harmless stuff like water and CO2. Okay, this sounds like a perfect solution, doesn't it? It's clean, it's powerful, it's literally sun-driven. But for a long time, this amazing technology had a huge, hidden flaw that kept it stuck in the lab.
Which, leads us to the big question. If we have these pollutant-destroying nanobots, why aren't all of our rivers and lakes sparkling clean by now? Well, the answer really comes down to a single, kind of disappointing number.
Just 4 to 5%. That's it. That is the tiny sliver of the sun's energy, the UV part of the light spectrum, that the standard catalysts, like the very common titanium dioxide, could actually use. It's like having a solar panel that only works for about 5 minutes a day. Just not very efficient.
So this created two massive roadblocks. First, these catalysts were wasting almost all of the available sunlight. And second, even when they did manage to get energized, that tiny battery we talked about would often just short-circuit. The energy would fizzle out before it ever got a chance to power the cleanup. It was a great idea, for sure, but with a critical design flaw. But this is where the story gets really cool. Scientists didn't just give up on the idea. They decided to go back to the drawing board and build a better engine.
The big breakthrough came from a technique called doping. And no, it's not what it sounds like. In material science, doping just means you intentionally add tiny impurities. In this case, a few atoms of other metals like iron or silver, right into the catalyst's structure to completely change how it behaves. It's basically giving our little cleaning robot a major hardware and software upgrade.
And the results? Whoa, they are dramatic. Your standard catalyst, stuck with only UV light, maxing out around 51% efficiency, and it's always fighting that short-circuit problem. But the new, engineered catalysts, they can absorb the entire visible light spectrum. Their efficiency just skyrockets to over 80%, and that annoying short-circuiting problem, it's pretty much solved. And the performance data? Well, it tells the whole story right here. The original materials, they're hovering around 51% efficiency. But once you add that strategic doping, silver-doped catalysts jump to 80%, and the iron-doped ones hit an incredible 82% efficiency. That's not just a little improvement, that is a complete game changer. And hey, don't just take my word for it. As the researchers themselves put it, doped variants exhibit superiority. This wasn't just some small tweak, it was a fundamental fix. This smart engineering directly solved the exact problems that had been holding this technology back for decades.
So, we've done it. We've created a super catalyst. What does this actually mean for the future? Well, its potential goes way beyond just cleaning up industrial wastewater.
This same core technology can be adapted for a whole bunch of other amazing applications. I mean, imagine using it to literally scrub pollutants out of the air we breathe, or to convert captured carbon dioxide into clean fuels. We could even use it to split water to generate green hydrogen fuel, or to pull valuable metals out of waste streams. We're talking about a versatile platform for cleaning up the environment.
This breakthrough is what finally pushes photocatalysis from being just a cool lab experiment into a real-world tool that we can actually use. It's a technology that can directly help us reach global goals for clean water and sanitation by offering a scalable, sustainable solution that's powered by the sun. It's the bridge from a scientific idea to actual real-world impact.
And it really makes you wonder, right? By precisely tinkering with materials at the atomic level, we've turned a flawed concept into a seriously powerful environmental tool. If we can design tiny engines to literally eat pollution, what other massive challenges could we solve by thinking incredibly small?